Hello YouTube, welcome to the video. This is the LeetCode White Belt bringing you another LeetCode problem, inverting a binary tree. So now if you're new to the channel, these videos are geared to those who have little experience with LeetCoding and programming in general. So if that's you, you're here in the right place. So for this particular video, we'll be providing two different solutions as well as introducing the concept of a binary tree. And you can find the timestamps in the video itself. Now, let's begin. So now let's define what a binary tree is. A binary tree is a data structure in which you have 0 to n number of nodes within that tree itself. And when you start off with a binary tree, you're always given the tree node root. So the root of the binary tree is a node that is the first node in that binary tree. So in this example, it will be this node over here that has a value of 4. So now, every node in the binary tree, you have access to 3 different things. So the first thing that you have access to is the tree's value. So the tree value will either be like a number or a string or a character. And usually for these LeetCode questions, they're gonna be numbers, so integers. So now the second and third thing that you have access to for each node is the left node and the right node of a particular node. So now if you look at this example here, for 4, you have a pointer to the left node over here, and that's going to be pointing to a node that has a value of 2. And for the same 4, you have a pointer to its right node, and that right node will be a node with its value of 7. Okay? And now, another thing to point out is that in a tree, the last nodes over here, for this last row, these are known as leaf nodes. So leaf nodes are nodes in which there are no left and right subnodes. So over here, if you're at this 1 and you try to access the left node, that's going to give you null. So it's going to say if you try to node.left, it'll be equal to null. And the same thing for its right node as well. Okay, so now let's go through this tree just to hammer home the ideas. So now we're gonna try to print out the root.value, okay? So, if you remember, when we're given these LeetCode problems with trees, we're always given the root of the tree. So the root of the tree will be the first node in the tree. So now if we try to print out this root.value, we're gonna be given 4, okay? So that's the thing that we printed out over here. And then if you try to do the left, and we say left value, we'll say root.left, and then I think one thing to hammer home too is we'll be like tree node left equals to root.left. So when you do root.left, it's going to return you another node in the tree, right? So it's going to be returning you this node over here. And then if you want to print out that value, you can do left.val like this. Okay? And then you print and do this. Left value is 2, which is what we see over here. Okay? And the same thing can be done for the right one as well. So let's do something like print right value. And now let's do tree node right equals to root.right like this. And then we say right.val. Okay? So right.val is 7. So the thing that we want to hammer home is that when you do root.left, it's going to return you a new tree node, which is the same object that we saw for the root object as well. And then the same thing for the right as well. And now if you want to see the example of when we get a null, is then if you try to access this 1.left or the 1.right over here. So the way to get there is that let's go from root.left. So now we're going to be, from root.left will be here. And we do another left. Now we're going to be here. And now, if we do 1.left, this is going to be null. So now if we try to do .val like this is going to throw us a null pointer exception because null doesn't have a property value. Null is nothing. So when you try to access something from nothing, it's going to throw you a null pointer exception. So keep that in mind. Now let's try this out here. Null pointer exception, which is what we thought was going to happen. All right, so now that we know what a binary tree is, let's try to solve the problem that we're faced with. So it says, given the root of a binary tree, invert the tree and return its root. So over here, we see that the 4 remains in place from the input to the output, but the left node and the right node get swapped. So here, 2 was a left, and then it becomes the right afterwards, and then likewise, 7 was the right, but then afterwards 7 becomes the left in the output. So we need to figure out a way to swap the left and right nodes for every single node in this tree. So when you're given these binary tree problems, the best way to solve them is to first solve it for the most simple case, and then you want to extend your solution to be generic enough to handle as many nodes as you need to handle in the tree. So let's look at this 213 example and try to solve for it. So let's see. So what we want to do is essentially swap the left and right. So what we want to do first is let's hold on to the left and right nodes. And once we hold on to them both, we'll say that, hey, the left was the old right and the right is the old left, basically. So we'll say tree node left equals root.left and tree node right equals root.right. And now let's say root.left equals right and root.right equals left. So doing this, we're essentially swapping the left and right nodes of the tree. And then afterwards, we need to return the root. Right? And I think this would work, like this code here would work for this example, and we can try it out. So we'll go to the console and run the code. Okay, it's accepted for this input. But now if we look at the third example, the root is empty. So when you see this root is empty, that means that the root is actually going to be equal to null. And then if we see our code here, we have on line 18, we're saying root.left. And if the root is null and we try to say null.left, we're going to get a null pointer exception because null does not have a property left. So if we run this with the empty input, we get that null pointer exception right over here on line 18 as mentioned. So what we need to do is add some code to handle the case where the root is null. So we'll say that if root equals null, return null. And this is fine because in this example here, if the root is null, we'll just return it as the output, right? Because there's nothing to swap in that case. So now let's run it. And now we get the accepted input for that example. Now if we look at the first example, our code will probably give the wrong answer. And the reason why it'll give the wrong answer is because in our code, what we're doing is that we're only swapping the root's left and right nodes. But if you notice here, there are more nodes in the tree that we're not like evaluating basically. So when we run this code, we're only gonna see the 2 and 7 get swapped, but the 1 and 3 won't get swapped, and the 6 and 9 won't get swapped. So we're gonna get the wrong answer. So let's verify that out over here and run it. Right, so we get the wrong answer, but we see that the 7 and 2 was swapped, but the 6 and 9 and 1 and 3 weren't swapped if you compare it to the expected result. So now we need to think of a way to apply our swapping algorithm to all the nodes in the tree so that we can satisfy a generic solution for this problem. So what we can do to apply our algorithm to other nodes in the trees, we can use a technique called recursion. So what recursion is that inside your function, what you're gonna do is call the function again within the function. But this time when you call the function inside your function, you're gonna be passing different inputs so that when the function gets called again, it's gonna be evaluating different things. And thus you can do the swapping for different nodes in the tree. And we can probably get the right answer like doing something like that. So what I mean by that is that we go over here. So after we do the swapping, because we know that 4 4, 2, 7 have been like handled correctly. So what we're gonna do next is say that invert tree root.left and invert tree root.right. So by us adding this code here, so we're calling the original function again like this. But this time, instead of calling against root, what we're going to do is call it with the left node of the root. So when we come over here, so when we come to line 29, we'll be passing the left node, which will be 7. So then what's going to happen is that 7 is going to be called, and we're going to go to the top of this. We're going to go to the top over here. We're going to say that, okay, 7 is, this node is not null, so this won't evaluate. And then we'll get the left and right node of 7, which will be 9 and 6. We'll do the swapping, and then we'll call invert tree with root.left, which is going to be 9 in this case, right? Because 9 is the new left. And then when we enter 9, we come over here. 9 is not null, right? And then we get the root.left and root.right of 9. Those are going to be null. So then when you enter here, we swap the left and right, but we're swapping null with null, so nothing's gonna change. And then when you call invert tree with null, we're gonna enter here this line 19 root equals null and return null. So we exit out, and then we're over here, and then we enter line 30 with 9's right, which is also null. So that's also gonna return null later on. So when this finishes running, we're gonna return the root. That's going to return this 9 node right here. And then we come back to line 29 again, but this time back in the context where 7 was a node. So you keep doing that algorithm until you actually are swapping all the nodes. So it seems like a little bit complex, like to follow along, but when you run it, it's pretty magical, and it'll actually run, and it'll be the right answer like this. And then to hammer home the idea of like which nodes we're evaluating at each time, we can like print out the node value like this, and we'll say root.val. So what's gonna happen? So we're first at 4, makes sense. Then we're at 7, makes sense, because what we do here is we say root.left 7, and then we come to 9, which makes sense. And then 9 is null, 9 left is null, so that returns null, so we don't do anything. And then its right is also null, so we don't do anything again. And then we're back to the 7. We're back to the 7 execution, and then we go right of 7, which is 6. So that's why we go from 7, 9 to 6. And once 6 finishes, we go back to 4's execution, and we see that 4's right is 2. So that's why we go from 4, 7, 9, 6 to 2 afterwards. So the way that we're visiting each node is, I think this is known as pre-order traversal. We first do our evaluation on the root, and then we go left and right. So there's different ways you can traverse through a tree. So you can first go all the way left and then evaluate, then go right, or you can go evaluate, then go left and right, or you can go, what was the last one? Left, right, and then root. So for this example, we can just keep it simple and stick to this type of traversal that we're doing here, and this will give us the right answer. So I think the main takeaways from doing this type of like recursion is that, first you want to be able to solve for the most basic case, and the basic case here is like a simple tree where you only have like these 3 nodes, like a root and 2 children, like that. Once you solve for that, you also then want to be able to handle cases where the root is null. So when you add that in conjunction with the simple case, then you can start to add recursion on top of that. Because when you call your function again, and you are handling that null case, you have a way that you can exit out of that recursion, like infinite loops essentially. Because if we didn't have this, well, first we get a null pointer exception eventually, but we also need some sort of way to break out of our like invocation chain, basically. Right, so that's basically how we do the recursion method. So if we think about like what the runtime complexity is, over here we're visiting each node once. So the runtime is O of n, where n is the number of nodes. And now if you're asked about like what the memory consumption is going to be, that's also going to be O of n. So the reason why that's also O of n is because every time you enter this invert tree like function call, you're creating a new stack on the actual like code execution. Like when the CPU is running, it's going to create a new stack so that you can actually like call your function. So yeah, I think one thing just to know, like whenever you're doing recursion, just know that you're gonna probably be doing at least O of n extra memory essentially, due to the fact that you're creating a new stack for every function call. So now that we solved this question using recursion, let's try to see if we can use an iterative approach to solving this binary tree question. So the difference between recursion and iteration when we deal with binary trees is that when we traverse each node in recursion, we were using the same function and calling it again within the function, right? So now in iteration, what we're gonna do is we're gonna use a while loop to be able to go through each node one by one by one by one. So in order to do that, this iterative approach, we need to leverage some data structures that allows us to like put in nodes one by one into some container, and be able to remove nodes from the container and put nodes into the container in such a manner that allows us to like evaluate the nodes that we care about. So the data structure that we can use in the iterative approach is, one of them is going to be called a queue. So the way that the queue works is that you declare it like this, equals new linked list. So okay, so now it's going to be empty, right? So you can think of it as an array basically, and the key properties are adding things into the queue and removing things from the queue. So what you add into the queue, whatever the first thing you add to the queue, and then when you later on call removed, the first thing you added to the queue will be the thing that gets removed. So it's known as first in, first out, FIFO. All right. So let's say we added queue.add root like this. Now the queue is gonna have a node with 4 inside of it. All right, and then we can say tree node removed equals queue.poll like this. Poll is the queue's method to remove something from the queue, or remove the first thing that you added to the queue. So the first thing we added was the root, so we just removed the root, and now the queue is empty, and now we have a reference to remove. So what we can do later on is say queue.add remove.left and queue.add remove.right. So that's going to be adding, let's like in this example, 2 and 7 like this. So now we have 2 and 7 in the queue, right? And then if we say tree node removed equals queue.poll again, like this. The queue is gonna have only 7 now, but the removed is gonna be 2, right? Because that was the first thing that was added. And then if we do queue.add remove.left, queue.add remove.right, it's gonna be 7 and then 1 and 3, right? Because 2 was removed and we added 2's left and right over here. And then when we remove 7 later on, what's gonna happen is that, and we try to add like 7's left and right, we'll be adding 6 and 9 like this. So if you look at the way that we're actually going through each node in the queue, the way that it is that we are essentially going through the tree row by row, right? So we first are at 4, then we're at 2 and 7, then we are at 1, 3, 6, and 9 basically. So this path is, or this like the way that we're going through this tree is known as a breadth first search, and essentially that means that we're going through the tree row by row. And in this case, it's being done left to right because we're adding things over here, left and then dot right like this. So then if we know this sort of like traversal algorithm, what we can now do is that once we remove the node from the queue, we can just apply our swapping thing that we did previously, and then later on add the left and right to the queue, and keep adding the left and right to the queue until we reach a null node like over here, and then we won't add that to the queue, and then eventually the queue will be empty, and then we can just return the root that we had previously. So let's see how we can do this. Okay. So let's start off with if root equals null, return null. So like that's the null check that we had previously. I think that can come in handy. It may not, but it doesn't hurt to add it. So we'll say if queue is empty equals to false. Tree node removed. Okay, so actually this shouldn't be if, this should be while, right? Because we want to keep going through each node in the tree one by one. So we want to keep adding things into the queue until we reach no more nodes in the tree. So we'll say tree node removed equals queue.poll. So the first iteration of the while loop, that's going to be 4 here. So we removed 4 from the queue, and then we say if remove does not equal null, do the swapping. Now the reason why we're adding this null check over here, because eventually we'll reach this 9 over here, and then we'll be trying to add its left and right, and when we add its left and right into the queue, we don't want to do any evaluation if the node is null. So let's now do the swapping. So we'll say tree node left equals remove dot left, tree node right equals remove dot right, remove dot left equals right, remove dot right equals left. Now we'll add, nope, we want to add the removed like this. Okay, and then we return the root later on after this finishes running. So the way that this is gonna run is, let's add like a print statement so that we can like hammer home the idea. Printing. So the way that this, okay, so accepted answer. So the way that this works is that we first add the root to the queue, okay? Then we remove it over here. It's not null, so we print it out, and then we swap the left and right. So now its left is 7 and its right is 2. Then we add the left and right to the queue. So then we add 7 and 2. So that's why the next thing in the queue is going to be 7. And then the next thing in the queue, and after 7 is going to be 2. So then when we remove 7 from the queue, we add 9 and 6. And then when we remove 2 from the queue, it's going to be 3 and 1 after we do the swapping. And then eventually when we add 9, after we remove 9 and we try to add its left and right is going to be null, so we don't do any of this swapping logic, and we don't add anything additional to the queue. So eventually the queue is going to be empty, and thus we're going to be able to exit out of this while loop. Okay, and yeah, and then we were able to return the root, which gives us the result. So let's submit this answer and see if it's the accepted one. Right, success. It ran in 8 milliseconds. So now if we try to evaluate what the runtime complexity is, this is going to be O of n, which is the number of nodes in the tree. The reason why is because we're going through each node one by one in the queue. And now if we try to evaluate what the the memory consumption is, like what the memory O of n is, that's also going to be O of n. The reason why is because we're in the worst case, we're going to be adding n number of nodes to the queue. So so basically the answer of like what the memory consumption is going to be however big the queue is that we're dealing with. Okay, so I think the main takeaways when you're doing the iterative approach is that if you want to go through the tree row by row, use a queue, and before you enter your while loop over here, first add the root to the queue, and then add this empty check over here, and then add this null check after you remove the first thing, like after you remove the first in first out from the queue, like this, after you do this pull method. Check if it's null, because if you eventually you want some sort of way where you can stop like going through these loops in your while check, because eventually the remove is going to be null, and you don't want to add that to the queue because you don't want to like swap for the null, and you want to be able to exit out of that while loop. And yeah, and I think that's about it, and you can just return the root like that and get the right answer. So I hope you guys found this video informative. If you guys did, leave a like and subscribe, and I'll see you guys in the next one. Thanks.